Okay. All right. So we started to talk about photon on Wednesday, and this is sort of, in some sense, the highlight of the course. So I'd like to make sure that everybody gets it. So I'd like to repeat some of the basic steps involved in how to get photons out of the Maxwell equations. So we started to talk about the process that involves emission of photon. So what we did is to take the Lagrangian you have seen before, where you could rederive the Maxwell's equation from. So we know this Lagrangian has the right content for us, for the electromagnetism. And we took the Coulomb gauge. And within the Coulomb gauge is actually give you a lot of simplification because the Gauss's law fixes the scalar potential completely for a given charge density at any given moment. So we can actually let this aside and just focus on the vector potential and quantize that part of the Lagrangian. So all you have to do now is to rewrite this Lagrangian specifically for the vector potential. And using the fact that the divergence of A vanishes, you can also simplify this part B squared in this particular expression down here. So once you have this expression, then you basically see that this looks very similar to harmonic oscillator in quantum mechanics. So A corresponds to X, and here you have X dot X dot, just like the kinetic energy for the harmonic oscillator. And in the second term, basically is the analog of the potential energy, because once you actually go to momentum space, this derivative just turns into the wave vector. So you have wave vector squared times x squared. So that's the analog of half m omega squared x squared in harmonic oscillator. So that's why we know how to quantize this. So the idea is that A, being basically X in harmonic oscillator, turns out to be a linear combination of creation and annihilation operator. And A dot, that's the analog of P, would end up being creation minus annihilation operator. And that's what we actually did straight ahead in this expression. And so this funny prefactor has to do with the fact that we wanted to get the correct normalization for the commutation relations between annihilation and creation operators at the end of the day. So, but idea is what I just said. So A is meant to be X of harmonic oscillator. So it's a sum of annihilation and creation operator. And A dot is supposed to be the analog of P in harmonic oscillator. So it's the difference between annihilation and creation operator. So that's the way we expanded this field operator A in terms of creation annihilation operator. And just a little notation here is that this omega P down here is the angular frequency of the photon. So WE, a relationship, tells you that h bar times angular frequency is the energy of the photon. But we also know from the relativity that for a massless particle like a photon, energy of the particle is the speed of light times the magnitude of the momentum. So that's the expression down here. So using this expansion, we can actually verify the canonical commutation relation. So from this Lagrangian, we got this vector potential to be the variable or coordinate of the canonical formulation. And by taking the derivative of the Lagrangian with respect to the time derivative of the canonical coordinate, you get the canonically conjugate momentum for it. And so that's how you know that this is the right commutation relation between A and A dot. And once you know this commutation relation, and once you expand A and A dot in terms of this little a and little a dagger, you can work out the commutation relation between little a and little a dagger. And that turns out to be the kind of ones we want. Namely, I have three components for A. I goes from 1 to 3, or X, Y, and Z. And for each component of A dagger is basically 1. And we chose this box normalization that whole system is in a cube where each side of is L. So within this box, the momenta are quantized in the unit of 2 pi h bar over L, as we have seen many times by now. So this canonical commutation relation tells you that they do not commute only when two momenta are the same. So that's the familiar form of the commutation relation for the creation relation operators. So we know exactly how to build the Hilbert space for them. And one little complication we had was the fact that the Coulomb gauge actually not makes all three components of vector potential linearly independent from each other. So by using this relationship, named that the divergence of A should vanish, I act divergence on this expansion in this vector potential, and derivative pulls out this momentum vector from the exponent. So what you find is that P dot A has to vanish. So that's why we have to write A, not in terms of three independent components, but the linear combination of only two linearly independent components, because it has to be orthogonal to the momentum vector. So that's where we introduce this idea called the polarization vector. So if you use the polar coordinates for describing the momentum vector using magnitude p, the polar angle theta and azimuthal angle phi, you can take a basis for this polarization vector in such a fashion to make sure that both of them are really orthogonal to the momentum vector. But as we emphasized already, the choice of these basis vectors for the polarization vectors is somewhat arbitrary, because it can be any two linearly independent vectors on a plane that is perpendicular to the direction of the momentum. So there is some arbitrariness in choosing these bases of the polarization vectors. And in particular, we talked about the one common choice is to use this kind of basis that basically corresponds to two orthogonal the vectors like this. So they correspond to what is called the linear polarization vectors. Or you can take linear combination between them to make it in a circular polarization, actually rotating clockwise and anti-clockwise. So there are two well-known choices for the polarization vectors, linear versus the circular. But in principle, there's an infinite number of choices for the basis vectors. So you basically pick whatever you like to make sure that two vectors are orthonormal and have to be perpendicular to the direction of the momentum. So that's what we did over here. So as a result, you end up with the this expression. So the vector potential is now expanded in terms of annihilation and creation operators. And we don't have three linearly independent components anymore because the Coulomb gauge condition, we have only two. So this subscript lambda runs only from 1 to 2. And for each lambda, there is a specific the polarization vectors. And correspondingly, I have A dot for it. And using the this expression, so this commutation relation between the annihilation creation operator remains the same. And that's when you know that the system is now a system of just the photons we wanted to get from this. And you can also work out the Hamiltonian for this system, which is basically E squared plus B squared. And if you just plug in these expressions for A and A dot into this, you can verify that it is really just a collection of a bunch of photons. So A dagger A is the number operator we're familiar with for each polarization lambda and momentum P. And for the corresponding number of the photons, each photon gives you energy given by h bar omega p, as we just talked about a minute ago. So that's the angular frequency times h bar. That's the energy of individual photon. So now you start to see that this system of the Lagrangian we talked about really does represent the system of the photons. And from this, we can construct the Fock space. The vacuum state is the usual one, namely has to be annihilated by the annihilation operator of every momentum and polarization. And then you start building the states with photons in it. So you act the creation operator to get one photon state, two creation operators to get two photon state, three photon states, and so on and so forth. And so the rest of the process is exactly like what we have done for the Schrodinger field. So I hope conceptually this makes sense. The only complications we have to go through are the facts that first, the vector potential comes in three components. And second, we have to make sure that gauge condition is properly satisfied. But apart from these two complications, everything we have done is the exact same steps we have done with the non-relativistic Schrodinger field. So that's the point I wanted to review just once again to see that actually sort of sinks in your mind and everything hopefully makes sense. Okay, let me stop here for this review part of what we discussed already on Wednesday to see if you have any questions on this. Everybody happy? Good. So one slide I failed to show on Wednesday is the fireworks, right? So this is really the moment to have a joy that you actually are happy to see photons now. Okay, so now that we have seen the photons, we wanted to use the photon to describe a process where you can emit a photon. So that's when we actually went back to the coupling of the point particle. So you all know that Hamiltonian for point particle coupled to the electromagnetism has this momentum now together with this vector potential here. And you have already seen that this combination is an important combination to make sure that it is covariant under the gauge transformation. And you also have the scalar potential that goes together with the time derivative, which again forms this combination of the covariant derivative, so that Schrodinger equation was covariant under the gauge transformation. So you have seen this expression already many times. But now, big difference from what we have done before is that when you put A and phi in here, they used to be a classical external fields. When you have, for example, the hydrogen atom, phi was the Coulomb potential in the hydrogen atom. And when you have the magnetic field, like in Landau levels, then A was an external vector potential that reproduces the classical magnetic field. But now we learn that this vector potential has creation and annihilation operator in it. So this Hamiltonian that used to be just point particle Hamiltonian now has a lot more in it, namely that this Hamiltonian can create or annihilate a photon. And that's the aspect we're going to use today. So we all know the Hamiltonian is a time evolution operator. So Hamiltonian pushes time forward. So once you have A with a creation operator in it, the time evolution can create a photon. And that's, so we need to see how exactly we are going to do this. So, but we know, at least have the idea that using this Hamiltonian that has the creation and annihilation operator in it, we hope to describe a process that you have a transition of, let's say, an excited state of a hydrogen atom in 2p that decays into the ground state oneness by emitting a photon. And so we have all this sequence of different transitions you can have in the hydrogen spectrum. And so what we're looking at is a simplest example of n equal 2 in a p orbital decaying down to the ground state of n equal 1 in the s orbital. So we'd like to use this Hamiltonian, now that there's a creation operator photon in it, to describe this process of the transition. And so I started to talk about this on Wednesday, and I just flashed how it might go. But now I'd like to go slowly, step by step, to tell you how exactly we actually go about and compute this process. At the end of the day, what we like to get out of it is to compute the lifetime of the 2p state, because it decays into 1s state in a photon. So the lifetime becomes a physical observable. And that's something I'd like to show how to compute using Fermi's golden rule. So that's what I'm getting at today. So any questions at this stage?
I just had a question. Maybe it wasn't covered in my quantum mechanics class, but
Okay.
why do we replace the momentum with the momentum minus, the electric charge times the vector field?
Okay, so that's also in the lecture note in photons.pdf. If you have a point
Okay.
particle Lagrangian, you can actually derive this. And of course,
Okay.
this combination makes sense because it showed the covariance and the gauge transformation. But you're right, we should be able to actually derive it, right? So the idea is that the point particle Lagrangian has this term that basically goes like E A dot X dot. So if you take the X dot derivative to derive the canonically conjugate momentum to it, so A dot X dot piece would give you additional contribution to the definition of the conjugate momentum. So that's exactly how this EA term arises in combined together with the canonically conjugate momentum P. And
Okay.
and I hope you look at it. And if it's still not clear from looking at the lecture notes, ask the question again.
Okay, sure. No problem.
Okay. Any other questions here? Okay, everybody seems to be happy. So now we're going to actually use this Hamiltonian to compute this process of emitting a photon from atomic de-excitation. So what we use is this famous Fermi's golden rule, which I hope you have seen in quantum mechanics class. If some of you have not seen it, can you raise your hand? I don't see anybody. Good. All right, so it looks like everybody has seen it before. So the idea is that we use actually perturbation theory now. You divide up your Hamiltonian into two pieces, and H naught is the Hamiltonian in our case for the hydrogen atom, and delta H is the correction to it, which we treat as a small perturbation to the system. And initial and final states are the eigenstates of H naught. And delta H is now a perturbation that causes a transition from initial state, which is an eigenstate of H naught, to another eigenstate F of H naught. And so this gamma Fi is the rate of transition, which is the same thing as to say that you actually have a transition from initial state to I to F, and gamma is the probability of the transition per unit time. And that's the definition of the word rate. So the rate of transition is the probability of the transition per unit time. So that's this quantity gamma. And so the idea of the Fermi's golden rule is that once you have this initial and final state, which are the eigenstates of H naught, for the case of hydrogen atom, you know exactly what the wave functions are. And using those wave functions, you compute the matrix element of this perturbation to the system, delta H. And that's the matrix element in here. You take absolute squared, and then you have the additional factors of 1 over H bar and the 2 pi times delta function that ensures the energy conservation. So that's the idea for the Fermi's golden rule. And in our case, we have this Hamiltonian given in terms of P minus EA squared over 2m plus E phi. And so I expand this out in the following fashion. The first piece is just take P out of this, the parentheses, so P squared of 2m. And phi, that's a Coulomb potential for us, is just the Coulomb potential coming from the proton, the nucleus of the hydrogen atom. So that's the zeroth order piece H naught. But then comes the rest of the terms by expanding this P minus EA squared in the power series in A. So the piece is linear in A are these two terms, P dot A, and the piece that's quadratic in A are the last term is the last term EA squared. So we identify this yellow piece as H naught, that's the unperturbed Hamiltonian, and the rest in cyan as the perturbation to the system. And here I've been a little careful here because A is a function of the position, and position is an operator for the position of the electron. So that position may not commute with P. So when I expanded out this square, I was careful paying attention to the fact that P and A can come with two opposite orderings. So that's why I have P dot A and A dot P separate. And then A, of course, commutes with itself. So the A squared is not ambiguous. So it's just a square of the A operator. So that's the cyan piece. So the rest of the discussion is basically how we compute the matrix element of this piece in cyan, knowing that I and F are the eigenstates of this yellow piece, which is just the plane of the hydrogen atom energy levels in the quantum mechanics. Okay, so I hope the plan is clear. Any questions about this? And I see a chat. Fiat flux. Very good, very good. Let there be light. No questions? Okay. So we go about and compute this matrix element. So delta H was this one coming from the previous slide. It turns out that, even though I was paying careful attention to the ordering between P and A, it turns out that I didn't have to, thanks to the choice of the Coulomb gauge. So when you look at the commutator between P and A, and summed over all the indices of P and A as an inner product, then P is basically the derivative with respect to X. So PA commutator turns into the derivative of A. But now that we are summing over all indices, that's the inner product here. So as a result, this is nothing but the Coulomb gauge condition, which vanishes. So it turns out that even though I paid this careful attention to the ordering between P and A, I didn't have to. So when I compute this matrix element here, I no longer pay attention to the ordering between P and A. And for this purpose, I'm looking at the process that initial state doesn't have a photon, but final state has a photon. And if you look at the A squared piece of the Hamiltonian, let me back up a little bit before masking it. The A squared piece has two powers of creation and annihilation operators of the photon. So this would change the number of photons by 2. And that's not what we need for this matrix element. So the only pieces we need to consider then are the pieces that is linear in A, and A has creation operator of the photon. So I only need that portion of this vector potential A so that I can create a photon in the final state from the initial state that does not have a photon. So that's why I mask this piece and focus only on the first two pieces over here. And then I remember how I write this vector potential in terms of creation and annihilation operators. And using the what we know already very well from the harmonic oscillator, then the matrix element of the vector potential from the vacuum state for the photon to a single photon state in the final state is just look at the annihilation, the creation operator over here, A lambda dagger. And so this A lambda dagger creates a particular photon with momentum P and polarization lambda. So the only piece that survives in this matrix element is when I pick P and lambda to be the same as the photon you have in the final state. So out of this big sum over all possible momenta and all possible polarization states, the only piece that would contribute to this matrix element is the piece that has exactly the right momentum and right polarization vector. So picking only that creation operator, I just keep the rest of the factors. So I have this prefactor in square root, which was necessary to guarantee that the A and A dagger have the correct commutation relations to build up the Fock space. I have this polarization vector and this plane wave factor e to the minus q dot x. So that's what I have over here. Just in case you're wondering why I have this complex conjugation here, which I didn't have over here, you know, I probably should have put complex conjugation here anyway, but we are using planar polarization where polarization vector is real, then you don't need to pay attention to that. But just in case, you might also want to do the calculation in circular polarization. Then circular polarization has this polarization vector, which is the linear combination of two of them with I between them. So it does matter whether you have complex conjugation or not. So if you use those circular polarization vectors, you need to put star here to make sure that the vector potential is a Hermitian operator, right? So here I have epsilon times A. To make sure that the vector potential is Hermitian, I need to make sure that this is exactly Hermitian conjugate of the first term, which means this epsilon needs to have a complex conjugate. So if you're using the linear polarization, it doesn't matter. But just in case you might want to use also circular polarization, then you have to pay attention to the fact that polarization vector here is supposed to be complex conjugated of the polarization vector over here. So that's just one extra thing you might want to pay attention to. But for now, we don't need to because we're using actually the linear polarization. Okay, so now that we know how to compute the matrix element of this vector potential out of here, between 0 photon state and 1 photon state, which is just given by this combination, then I just keep the rest, namely E, P over M between 2P and 1S state. And that's this thing over here. So I kept this polarization vector, complex conjugated, and this prefactor with the square root up here. And then I have this P over M coming from this Hamiltonian, and I put the minus sign up front over here. And now that I don't have to pay attention between the two, I cancel the factor of 2 downstairs. So that's why there's no factor of 2 downstairs. And I have P. And one thing you have to keep in mind, though, is that this vector potential is evaluated where the electron is, namely that argument x of the vector potential is the x operator of the electron. So I have to keep this the plane wave factor, e to the minus iq dot x, still sandwiched between the 2p and 1s states of the electron. So x has to be in this matrix element. I can't take this out. So that's the one little complication you need to be aware of. But at the end of the day, again, it doesn't matter within approximation we are going to use. But for to be totally correct, I need to keep this e to the minus iq dot x factor in the matrix element of the Hilbert space of the electron sandwiched between initial state 2p and final state 1s. Okay, so I believe everything is straightforward. There are many steps involved. So let me stop here once again to see if we have any questions. Everybody happy? Okay. Oh, George, you want to speak? No? Okay. So let me then proceed. Oh, go ahead.
I had a very brief thing. So the P momentum operator we have sandwiched between 1s and 2p, that is the particle momentum operator, correct?
Yes.
And
yes.
then the Q we have here is actually the photon momentum operator.
That's right. And because the Q is specified by the final state, this is actually already a number. It's the momentum of the photon I specified for the final state is stuck in here. So Q is already a number as far as this matrix element is concerned, but X is an operator for the position of the electron.
Okay, I see.
Okay. Any further questions here?
Yeah, I was just wondering, could you repeat the reason why we're leaving off this last term in the perturbation?
Oh, this one, yeah. So the idea is that this last term has a squared in it. And A has annihilation operator and creation operator. And if you take a squared, I have three kinds of terms. One is this a squared, little a squared, that annihilates 2 photons. Another one is a dagger squared that creates 2 photons. And the cross term, a dagger, that creates photon and annihilates it, so it doesn't change the number of photons. So from vector potential squared, I have 3 pieces that changes the photon numbers by -2, +2, or 0. But in this matrix element, I'm supposed to change the number of photons by 1, starting from no photon, 0, to 1 photon, 1. So I need to look at the piece of the operator that changes the photon numbers by 1. A squared has none of the pieces that would do that, because it's either 2 minus 2 or 0, not 1. On the other hand, first 2 terms here has linear power in A, which does have a piece which is the creation operator photon that changes the photon number by 1. So first 2 pieces will give you non-zero contribution to this matrix element, but the last term here does not, and that's why I can drop it. Does that answer your question, Anna?
Yeah, thanks.
Okay. Any further questions?
And then,
okay, go
sorry,
ahead.
just one
more. Go ahead.
Clarifying question on the algebra. So when we are taking the inner product between kind of the overlap integral between the vacuum state and this like 1 photon
this
state.
One. Okay, the bottom.
Yeah. So, okay, so we can just get rid of the terms with the annihilation operator because we're acting
Right.
on vacuum
That's
state,
right.
and that's why we
Right.
just have the complex conjugate term.
That's
Okay.
right.
Okay.
Well, thanks for asking. Yep. So that's how we get this expression over here. Then you see the rest is just to work out what this matrix element is, knowing the wave functions of the energy levels of the hydrogen atom. So the rest, in some sense, is a straightforward problem from quantum mechanics, which still requires some algebra and integral, but nonetheless, I hope that conceptually the rest is straightforward. Okay. And it's also worth emphasizing here that this is the first time we looked at the process where number of particles changes. So in non-relativistic Schrodinger field theory, the Lagrangian nor Hamiltonian had any terms that would change the number of particles in it. But here I have a Hamiltonian where number of particles does change, number of photons does change. So this is the first time you're looking at a process where number of particles does change. Initial state has single electron, final state has another electron and a photon. So we increase the number of particles by 1. But the formulation of quantum field theory already told us how to actually go about and compute that kind of transition amplitude. So formulation-wise, I have not introduced any new ingredients. I just followed through exactly what we have done with the Schrodinger field theory. We identify canonical conjugate momentum. We set up the canonical commutation relation. We expand the field in terms of the momentum modes. So none of the things are new as far as conceptual steps are involved. But following through the same steps and knowing what the Hamiltonian is for a particle, we already have a term that requires the change of the number of photons in it. And so I just used it for the purpose of computing this matrix element. So the quantum field theory, in some sense, knew already what we are supposed to do. And so we are just following through the process now to compute this new process of changing the number of photons between initial and final state. Okay, so let me then just go ahead and compute this matrix element. And eventually we just stuck in the matrix element into the Fermi's golden rule. So there is a great simplification here. So even though I did emphasize that this plane wave factor e to the minus q dot x has to be kept inside this matrix element because x is an operator, but it turns out that it's a good approximation to ignore it. The reason being that q is a small number because q dot x will give you a contribution which is very much suppressed relative to 1. They're suppressed by the fine structure constant. And the way you can see it is by looking at the following very simple expressions you may or may not have seen before. So we know the fine structure constant is defined this way. The E squared over 4 pi epsilon naught, that's the combination that appears in Coulomb potential. And if you further divide this by h bar c, that becomes dimensionless. And you know alpha is 1 over 137. That's why physics 137 is the quantum mechanics, right? So the alpha fine structure constant is a small number. And it's actually very useful to rewrite the expression for the energy levels for the hydrogen atom using the fine structure constant. And you may not have seen this expression before, but let me.
Oh, I think you're muted.
Yeah, sorry, I was disconnected. Can you hear me now?
Yeah.
Okay. Am I kind of frozen? Do you see my moving hands? Oh boy. Hello? Is there still connection problem, you think?
There's.
Hello? Huh. Hello? Can you hear me? Hello?
Yeah.
Okay, so hopefully it's okay this time. Let me get back to slides, but it looks like I'm having a connection problem, so it might happen again, just in case that you should be warned on that. So let me share the screen again. And I was looking at this slide over here. I'm waiting for the screen to show. Okay, good, good. So I started to look into the decay rate, and I was just about to explain why I can ignore this plane wave factor in the exponent here. And that's because Q dot X turns out to be of the order of the fine structure constant, which you know is much smaller than 1. And so idea is that you can write energy levels of the hydrogen atom using the fine structure constant in this fashion. So M, of course, is the mass of the electron, or to be more correct, the reduced mass of the hydrogen atom. MC squared, as you all know, has a dimension of energy, and alpha is dimensionless. So energy levels of the hydrogen atom can be written this way. So MC squared takes care of the overall mass energy dimension. Alpha squared is dimensionless, and N is the principal quantum number of the hydrogen atom, together with a factor of 2. So this is just yet another way of writing the energy levels of the hydrogen atom, so you know how things go together with the fine structure constant alpha. And using the same idea, I can also write the Bohr radius using alpha. So h bar over mc is what is called the Compton wavelength. So this combination has the dimension of the length. And again, alpha is dimensionless, so this whole thing also has the dimension of the length. And it sort of makes sense. When alpha is small, then the Coulomb attraction is small, so energy levels, binding energy is also small. So it makes sense that it goes like alpha squared. In the same way, when the alpha is small, then the binding is weak, so the radius of the bound state will be large. So it is indeed goes like 1 over alpha. So this is just another way of writing the energy levels of hydrogen atom and Bohr radius using the mass and alpha. And knowing these expressions, I can estimate what this Q dot X is. Q is the momentum of the photon, which is the energy over the speed of light. And energy of the photon corresponds to the energy difference between 2p and 1s energy levels, because the delta function in Fermi's golden rule would enforce the energy conservation. So 2p minus 1s is given in terms of this expression over here, which is order alpha squared. On the other hand, Bohr radius, as we have just talked about, goes like 1 over alpha. So this 1 over alpha cancels one factor of alpha from the energy levels, but another factor of alpha remains. So at the end of the day, this whole combination will be order alpha, which we know is a very small number. So Q dot X is actually negligible when you expand this exponential in terms of 1 minus I Q dot X of H bar, and then 1 squared and so on. So I can ignore all the high order terms because they are suppressed by higher powers in alpha. So the only thing I need to keep is 1 out of the theta expansion for this plane wave factor. So at the end of the day, it didn't matter that I actually kept this exponential factor inside this matrix element. So I can ignore it. So I mask it. And another little trick I'm going to use is to rewrite this momentum operator using position operator. So we know what we are doing is the perturbation theory, and initial and final states are the eigenstates of this unperturbed Hamiltonian H naught. And using this H naught, I can rewrite this P over M as a commutator of X and this unperturbed Hamiltonian. So that's fairly easy to check. So if I look at the commutator of X with this H naught over here, the second term, Coulomb potential, is a function of X. The R is, of course, magnitude of X. So it commutes with X operator. but p squared over 2m does not. So what I need to look at then is xp commutator, that's IH bar, that's canceled by IH bar downstairs. And I have 2 powers of p, so I get factor of 2, that cancels 2 downstairs. And an end result is p over m. Namely, this xh0 commutator over IH bar is nothing but p over m. Then I use the fact that 2p and 1s states are the eigenstate of H0 operator. So when I have this commutator in this ordering xh0, H0 acts directly on 2p state that pulls out the eigenvalue energy of the 2p state. And minus the opposite ordering between H0 and x, then H0 acts directly on the bra 1s. So that pulls out the energy eigenvalue energy of the 1s state. So end result is that this commutator is the energy difference over IH bar over here with EX remaining inside this matrix element. And X, as you remember, is the position of the electron relative to the position of the nucleus, the proton in the case of hydrogen. So this is the vector that stretches from positive energy, charge to negative charge, namely that this is nothing but the electric dipole moment operator. To be correct, should be as a minus sign here, but nonetheless, this is the electric dipole operator. So the idea here is that this is said to be a dipole transition, namely that you start from initial state of hydrogen atom, making transition to the final state of the hydrogen atom through an operator, which is the electric dipole operator, EX. So by ignoring this exponential factor, I end up with a matrix element which has only the dipole operator in it. And so this is called a dipole approximation by ignoring these higher powers in alpha. So idea now is very simple. You have this Coulomb potential, the hydrogen atom systems, and you know the wave function 2p state, you know the wave function 1s state in coordinate space, and EX is also an operator in coordinate space. So you just put these wave functions together, stick in EX in between, then do the position space integral to compute this matrix element, then you are done in terms of computing the matrix element. Then you stick that into this formula for the Fermi's golden rule, and then sum over the final states over all possible momenta of the photons and all the possible polarization states of the photons. Then you can compute the decay rate of the 2p state to whatever state that it would end up with. Okay, let me pause here again to see if there are any questions on this.
In position space, the X operator just becomes like the, I guess, the vector sum of each of its components, right? So
that's right.
The integral is like right in that case.
Calculate. Right. So that is going to be shown on the next slide. Well, all I have to do then is to write down the wave function of 2p state in coordinate space, write down the wave function of 1s state in coordinate space, and to compute the matrix element, I'm supposed to do x integral over it. And in the x integral, I stick in this EX. And the index of this vector is contracted with this polarization vector over here. So I need to keep track of the polarization vector too. But it turns out in simple calculation I'm going to do, I also need to take only one of the polarization vectors because the other one doesn't contribute. So the calculation ends up being actually pretty simple. Does that answer your question, Sahil?
Yeah.
Okay. Any other questions here? By the way, this kind of expression for the energy levels is very convenient because once you know mc squared is 0.5 million electron volt, and alpha is 1 over 137, you can immediately work out that the energy of the 1s state is minus 13.6 eV. So I really encourage you to actually remember this formula, which comes in handy whenever you think about some physics problems. All right, any further questions here? Good, so let me proceed. So once again, there are many steps involved in this calculation, but I hope every step is conceptually simple and clear. And of course, you need to go through every steps of it, so it might look a little overwhelming at the end of the day, but I'm trying to make sure that every step is clear so that we can move with confidence to the next steps to complete the calculation. So now what we need to do is to compute this matrix element so that I can stick that into this Fermi's golden rule, which now requires computation of this matrix element between 2p state and 1s state of the operator, which is the electric dipole operator. And at the end of the day, we also need to sum over the final states. So I just rewrote this Fermi's golden rule, knowing that what I'm computing is this matrix element, which is yet to be computed on the next slide. And so I stick in this expression in here. I already took this square of this square root factor and put that up front over here. And then this delta function between initial and final state is given by this argument of the delta function. So initial state is 1s state energy, sorry, the 2p state of the energy of the hydrogen atom. Final state energy is the energy of the 1s state plus energy of the photon, which is given by the momentum, magnitude of the momentum, photon times speed of light. So that's the delta function, which enforces the energy conservation in this system. And in order to compute the decay rate or lifetime of the 2p state, I don't care what particular momentum of the photon is emitted. So I sum over all possible momenta of the photons in the final state to compute the decay rate of the 2p state. So that's here. So I would like to compute the decay rate of the 2p state by summing over all possible momenta and polarizations of the final state photons. And we have learned already how to sum over momentum states in the limit where box size is large. So this is just the way you count the number of momentum modes, which you have seen before. But fortunately, you see the end result doesn't depend on the size of the box, because the way you sum over all possible momentum modes has L cubed in it. But the prefactor here has 1 over L cubed in it, so they cancel. And that's, of course, in some sense by design of the box normalization. In the large box size limit, the physics should depend on what you think is the size of your experimental apparatus. So it should be clear why the dependence on L cube would cancel out at the end of the day. But it is gratifying to see that indeed that does happen by looking at the simple expression over here. So I stick in this the transition rate gamma fi into the integrand, cancel L cube factor, keep track of everything else. So it looks like this. And I also rewrote this three-dimensional integral over the photon momentum into the polar coordinates. And the reason is clear. By looking at the polar coordinates, one of the integral is over the magnitude of momentum of the photon. On the other hand, the delta function here also depends only on the magnitude of the photon momentum. So by writing it this way, I can immediately perform integral over the magnitude of momentum of the photon using this delta function. And one little thing you need to be aware of is once you have the delta function of c times q instead of q itself, you need to make sure that this c factor is taken care of. So this delta function of this argument is the same thing as delta function of q minus this expression over here with 1 over c in front of it. In general, when you have the delta function of a function of the variable, then that's the same thing as a delta function of that variable over derivative of that function. So I'm using that result. The derivative of this argument, which is a function of q, is c itself, and I divide the delta function by the derivative, and that's this factor c over here. So that's one little thing you need to be careful about. But now that you have paid attention to it, then I can just go ahead and do the integral over q. So q integral is now eliminated. And then I find this rather simple expression. I also did one more thing. This omega p was supposed to be the angular frequency of the photon. So if I multiply h bar, both on the numerator and the denominator, I have now h bar in the numerator. Denominator is h bar omega p. That's the energy of the photon. But now we are looking at the expression written as a function of q. I'd better write the energy of the photon as c times q once again. So this is just a simple rewriting of writing expression in favor of q instead of omega p, but I haven't changed anything over here. So what I have done is to do the q integral that eliminates this delta function. So this q integral is now gone. I still have q squared d omega for the solid angle numerator, 2 pi h bar cubed downstairs in the denominator. I still have the same matrix element squared, and I need to keep this 2 pi over c factor over here. So once again, on this slide, there are many steps involved, but every step, I hope, is conceptually clear, and nothing is complicated. It's just meant to be straightforward algebra of working out the Fermi's golden rule. But anyways, let me stop here again to see if there are any questions.
Will we eventually like substitute back in for like the q? Is evaluating the delta function, right? Like we have now q is equal to 2e of 2p minus e minus.
Right, that's right. So once we actually finish up the calculation, I keep q as a symbol throughout the calculations, but at the very end of the day, I replace q in terms of this energy difference between 2p and 1s state. Okay. Any further questions here?
How do we get the q square in front of dq?
That's just a rewriting of this d cubed q three-dimensional integral in polar coordinates.
Yeah, I see.
Thanks for asking. Any further questions here? Good. So now finally, we use the wave functions of 2p and 1s states to compute this part of the matrix element. So this is the simplification we have done, and we need to compute this matrix element between 2p and 1s state. And then we look at the case when initial state has the zero, what is called, I forgot the name for this. What is called the M? This is the Z component of the orbital angular momentum. Does anybody remember the name for it? Sorry. English, there's English one. Oh, magnetic quantum number. Thank you. So this magnetic quantum number M, I specifically look at the state when this is zero, just because that actually simplifies the calculation. And of course, rotational invariance of physics tells you that no matter which spin state I'm looking at, the decay rate has to be the same. So I'm just specifically looking at the case when this magnetic quantum number is zero, just because that gives me the simplest way of computing things. And when the magnetic quantum number vanishes, then this orbital angular momentum is sort of in the xy plane. So you have the azimuthal symmetry. So among three components of this electric dipole operator, Ex, the piece for the x direction and y direction just identically vanishes, because x direction is pointing in x direction, obviously, y is pointing in y direction. But because the state is azimuthally symmetric, there's no particular orientation in xy plane, which means that they have no particular orientation, and therefore their contributions vanish. which you can verify explicitly by sticking it into this integral. But you know ahead of the time from symmetry of the system that x and y components do vanish. So the only thing that remains to be computed then is the z component. And then you dust off the old quantum mechanics textbook, whatever book you like, open the book and find the wave functions for the 2p state. And here's the radial part of the wave function for 2p state, which comes with the spherical harmonics. And I specifically chose magnetic quantum number 0 here with the orbital angular momentum 1 because we're looking at the p state, right? So this is the wave function of the initial state in coordinate space. And the same here, this factor here is the radial, the wave function for the oneness state. Then you have the spherical harmonics for L equals 0 for the S state. And of course, the only possible magnetic quantum number is 0 for the S orbital. So this is the wave function for the final state in a coordinate space. And what I need to do is to compute the matrix element from this initial state wave function to final state wave function by sticking in the operator in between. And operator is E times Z. E is, I put this up front. Z is R cosine theta in a polar coordinates. And then I have the integral over the three-dimensional space. And A is the ball radius. I wrote AB on the previous slide, but I just kept it A simply over here. Does it mean the same thing? And the rest is just I need to perform this integral. And end result, I don't show the steps in here. You can just type it into Mathematica and the result just pops out. Is this simple factor over here. And it makes sense that final result has a dimension of E, the charge, times the ball radius, because that's exactly the dimension of this operator, E times Z, electric dipole moment. So it makes sense that end result has a dimension of charge times the distance. So that's the integral to get this matrix element. And it also turns out that even though I'm supposed to sum over all possible polarization states of the photon in the final state, I chose the basis in such a way that one of the polarization vectors has vanishing component in z direction. Because I'm supposed to dot this electric dipole operator with a polarization vector. Once I choose this EZ in z direction, that specifically chooses z component of the polarization vector. But for the second polarization vector, that identically vanishes. So I didn't need to compute this. The only polarization vector I need to keep is the first polarization vector, which does have finite, the z component. So by taking this choice of the zero magnetic quantum number for the initial state, I drastically made calculations simple. Only one component of the electric dipole moment operator contributes. And correspondingly, only one of the polarization states of the photon contributes. So I don't need to sum over the photon polarizations in a final state. So that gives me then this result. So the you can compare this to what expression on previous slide. Let me actually go back and show that once again. But this is basically the expression I had, except that now I have sticked in the matrix element. Now I have computed from this integral, and that's this factor over here, times the polarization vector, which is sine theta. I put it over here. And sine doesn't matter because I take absolute square of it. And the rest is exactly what I had on the previous slide. And just to make sure that you do actually can see that this is the same thing I had on the previous slide, just watch that this looks similar to what I had over here. This expression here, and the prefactor h bar over 2 epsilon naught CQ, and this post factor 2 pi over c is what remains in a finite expression I had. The only thing I did is to replace what's in this absolute squared by what I computed over here. And that's this thing inside this absolute squared. So once again, everything I'm doing is just straightforward algebra. There are many steps, and I may look overwhelming, but every step is very simple and conceptually nothing new. It's just a straightforward algebra. I hope you can see that. But anyway, let me stop here again to see if there are any questions on this. Is it okay? All right. And then what remains to be done is just perform this solid angle integral of sine theta squared. And this is the sort of the expression you might have seen for the dipole antenna in classical electromagnetism. So, if you have an antenna that receives the radio waves or emit the radio waves, then the antenna that has this long bar in it is a dipole, because the charged electrons inside this bar would go back and forth like this. That's a dipole. And then the antenna would emit the radio wave, which has this angular distribution that goes like sine squared. So the dependence on the angle is exactly what you may have seen, I don't know if you have done this, in a dipole emission of the radio wave from an antenna. So that's why this expression called dipole approximation makes sense in two senses. One of them is that it really is a dipole operator in it. And second, the angular distribution of the emitted photon really does follow the emission of the dipole wave coming from antenna, except that we are now looking at this as the individual photons. So as we learned in quantum mechanics class, each time photon would be detected a particular angle. But if you keep repeating this experiment, looking at the photons coming from the decay of 2p states, over time, you see many dots on the screen for the individual photon hits, but they end up forming this distribution of the probability distribution that goes like sine squared. So that's the meaning of this expression over here. But anyways, I do the angular integral now to get the final result of the total decay rate of the 2p state. And it's a very simple integral over theta. And again, I use this expressions I used before to write everything in terms of alpha to get a simple expression at the end of the day. And as Anna asked just a few minutes ago, I need to write Q now in terms of the energy difference between 2p and 1s state over speed of light c. So Q is E2p minus E1s over c. And then I know how to write it using alpha and m. So I replace every Q, which comes with the fifth power, 2 powers here, third power, 2 power here, 2 power here over Q. So that goes like Q cube. And I replace Q in terms of that expression. And I do the theta integral, the d omega of this sine squared. And everything then follows. And I also have this E in it, which is squared, together with the epsilon naught downstairs. So I can rewrite it in terms of alpha as well. So then everything turns into this. So sorry, I forgot to mention that this Q is actually written this way because it's a difference between 1s and 2p energies, and 2p part has this 1 over 2 squared in the expression. So, so that is an explicit way of writing it. And then by putting everything in there, I don't show the steps from here to there, but this is the end result. You get this funny fraction in front of it, but the rest of the dimension should make sense. So mc squared has the dimension of energy. Energy over h bar has dimension of 1 over time. Hence, this is the rate, probability per unit time. And alpha to the fifth power is a big power, but nonetheless, this is just dimensionless quantity because alpha is dimensionless. And you put all these numbers together and you find the prediction that the decay rate of the 2p state of the hydrogen atom is 6 times 10 to the 8th over second. So this is the probability of transition per unit time. And so what you can measure then, by looking at the decay of the hydrogen atom on 2p state, you measure this quantity which turns out to be this number. So you see an excellent agreement between what we computed in this dipole approximation with the measurement. If you want to really recover this precise, 5 digits of the measured value, then we have to do a little bit better job. We shouldn't use dipole approximation. We probably need to keep the higher orders. There may be some other corrections we have to get involved. The M has to be reduced mass instead of mass of the electron, and so on and so forth. But at least you see the overall agreement between the simple computation we have done with the measured value. And the meaning of this measured value of the rate of the decay is the usual decay law you see in, for example, radioactivity. So the number of 2p states, suppose you have gas of hydrogen atom, bunch of them in 2p states initially, you have number n of them, and you start to lose them because they start to decay into 1s state. And how much you lose per unit time is given by this decay rate for each of the atoms. So the right-hand side of the equation is this decay rate gamma times the number of atoms you have at that moment. And by integrating this simple differential equation, you find this exponential law of decays, which I'm sure you have seen before. And what is actually appears the time scale here is the lifetime of that state. And comparing this differential equation with the solution, you can identify that lifetime tau is just the inverse of gamma. And inverse of gamma we computed is 1.6 nanoseconds. So the way you interpret this calculation of the decay rate is that what you have computed is the inverse of the lifetime of the 2p state, which follows this exponential decay law, which I'm sure you have seen in freshman physics class. So that's what we were after. And we are now done with the computation, which then agrees beautifully with the measured lifetime of the 2p state of the hydrogen atom. Okay, so this is another moment for celebration. I don't have more fireworks now to show, but anyway, let me pause here, and I'm sure there are questions on this. Anna?
I guess, yeah, okay. So this is like if we just had an excited hydrogen atom without any external, except for the vector potential in the Newtonian. This is the lifetime of, this is the time we would expect it to stay in that state before it drops back
right.
down to the ground state.
That's right. And of course, over time, all of them would decay away down to the ground state, so you lose all of them. But how quickly you lose them is given by this lifetime, 1.6 nanoseconds. And as you said, this is the decay under no influence of external fields. So this is called spontaneous decay. And as opposed to the induced decay. So when you have heard about the laser, for example, and that is actually induced decay of excited levels, because when you produce additional photon, when you already have photons around you, then you are computing the matrix element of the creation operator from a state where you already have photons in it with n, and create another one going to n plus 1, and that matrix element is square root of n. So if you start with a state that already has lots of photons in it, then the transition amplitude is enhanced by square root n, and therefore transition rate is enhanced by n. So you have much more quick decays in the presence of additional photons around it, and then you say that's an induced emission, induced decay. Here I'm talking about the case where you don't have any photons around. That's why I computed the matrix element or creation operator from the vacuum state to 1 photon state. Because I'm starting with the vacuum state with no photons in it, that's not an induced decay. It's just that you have a single hydrogen atom in 2p state with no photons around it, which just decides to decay into ground state by emitting a photon. And then you say that's a spontaneous emission, spontaneous decay. So that's exactly the situation we are talking about here. So thanks for asking the question, Anna. That is a very important point to clarify. Any further questions on this?
Is this lifetime for an ensemble average? Because right now we only have like one electron, correct? And that actually has like a discrete jump time, but this would be over some sort of ensemble average, correct?
Yeah. So this is the same thing as the average lifetime. So again, this is quantum mechanics. So you can never predict at what moment a particular 2p hydrogen atom would decay. Each atom would decay at different moments. But if you actually have a collection of hydrogen atoms in 2p state, even though each one of them decay at different moments, you can identify how they line up to give you this exponential decay law over the ensemble. And once you find this overall ensemble, then you can compute the average lifetime of the decay. So you take the ensemble average of this exponential over time, and t integral of this exponential is of course nothing but tau. So that's how you find this tau in the exponent to be the average lifetime of the 2p hydrogen atom over the ensemble. So the reason why we call this tau as a lifetime, which appears in exponent, is precisely because of what you just said, Sahil, which is meant to be ensemble average of lifetimes of many hydrogen atom in 2p states. But that's what we usually refer to as the lifetime of the 2p state of the hydrogen atom. Does that answer your question?
Yeah, it does. Thanks.
Okay, thank you. Thank you for asking that question too. And I'm sure you have seen this exponential decay law earlier in some other physics classes, but this is where it's coming from. Now that you know how to compute these things from fundamental principles in quantum field theory, all you have to do is to use this decay rate, the probability per unit time. And the meaning of this probability per unit time is what appears in this right-hand side of the equation, where number decreases per unit time with that probability. And then you just integrate this differential equation so that this 1 over gamma goes into this exponent. And that's how you get this exponential decay law. And you know how to compute the lifetime of whatever state you like now. So even though I just focused on decay rate of the 2p state to the 1s state, now in principle, you can compute all of these things. So what is shown here is just schematics of the energy levels of the hydrogen atom. This is what we have just computed from 2p to 1s. But using the same dipole operator, you have the selection rule that dipole operator basically carries angular momentum of unit 1. So you can compute transitions where the angular momentum, the orbital angular momentum of the initial state and final states differ by 1. So you can compute, for example, this transition 2, or that transition 2 because L changes from 2 to 1. Or you can increase the angular momentum 2, like this in yellow. Do the same thing also for the n equal 4 states, decreasing angular momentum by 1, or increasing angular momentum by 1. And transitions are not limited from neighboring or the principal quantum numbers. You can jump from 3 to 1, 4 to 2, or all the way from 4 to 1. So you can compute all of these transitions now, knowing the energy levels and the wave functions of the hydrogen atom states. You just stick those into the same integral I have shown earlier on the slides, and you just perform the integral, stick that into the Fermi's golden rule, then you can compute the lifetimes of all of these states. And when you ask the question of what is the lifetime of 4p states, then of course you need to add over the final states. So you sum over the decay rates of 4p going to 3s with 1 photon, 4p going to 3d with 1 photon, 4p going to 2s with 1 photon, as well as 4p going to 1s with 1 photon. For each process, energy of photon, of course, is different. but you just sum over them, and that's you find the lifetime of the 4p state. But now you have also computed the probability of 4p state decaying into one particular final state as well, whether it goes to 3s, 3d, 2s, 1s. You can also compute what is called the partial lifetimes or partial decay rates, and you speak of branching fractions. What is the probability of 4p state decaying to 1s state? Is it 60%? And decaying to 3d state, maybe 20%. And so you can have now different branches of decays happening to all kinds of different final states. But now that I have shown you the schematics of the potential decays, you realize one strange thing over here. I don't have any arrow from 2s state going anywhere, because this transition from dipole transition has to change the angular momentum by 1 unit. So if 2s decays, it needs to go to a p state, but there's no p states below 2s state, so it doesn't happen. So now I have a poll, which I hope I can do. Polling, launch poll. So what happens to this 2s state? 4 choices. It doesn't decay. 2s state happens to be actually stable. Second, it decays because we actually ignored higher powers in x in the dipole approximation. Second, it doesn't decay into 1 photon. It requires decay into 2 photons instead. Fourth, there's something wrong with this idea. So maybe 2s state can never be populated experimentally. So just pick one. All right, I have 4 votes. Some of you are still thinking. Good. All right, so I have all of them. So here we go. 5 of you have chosen that once I keep the higher powers in x in exponential, it should have finite matrix element. Some of you also said that it decays into 2 photons instead of 1 photon. It turns out in this case, even if you include the higher multipoles, it does not lead to 2s decay, but it turns out that you actually need to consider final states with a 2 photons. So in this case, the second choice is the right answer. The way it happens is that if you look at Hamiltonian, I ignored this a squared piece before, right? Because I was interested in a final state with only 1 photon. But now I need to consider this piece as well, a squared in it, so that 2s state can decay by emitting 2 photons, sorry. So now I have a squared, and each a has creation operator of photon. A squared now has 2 powers of the creation operator of the photon. Using this last term of the Hamiltonian, I can describe a process where 2 photons are emitted. And so I have to consider that as well. But this is the point I have to tell you that we need to do a little bit of a more formulation, and I have to go through the formulation of time-dependent perturbation theory. Because when I consider decay of 2s state to 1s state by emitting 2 photons, not only that I should use the first power of the third term in the perturbation Hamiltonian, I also need to consider second order in perturbation coming from the first 2 terms. And Fermi's golden rule is only the first order result in perturbation theory. I need to keep track of second order in perturbation theory too, which goes beyond the Fermi's golden rule. I have to generalize the Fermi's golden rule to the higher powers in perturbation. So I need to go through that formulation before I can use the Fermi's golden rule with the generalization to second order to actually compute this process of 2p going to 1s by emitting 2 photons. So that's why I start discussing the time-dependent perturbation theory next week. Reggie actually covered this already in discussion section earlier this week. So if you have attended it, you have already some idea on how that works. But let me go through that anyway so that everybody would see it. So I go through the formulation of time-dependent perturbation theory first next week. And once I have the formulation, then I can compute the decay rate of the 2p state, as 2s state as well. And once I'm equipped with time-dependent perturbation theory, I can also compute, for example, scattering process of photon scattered by an atom, the Rayleigh scattering, you might have heard of it, using the time-dependent perturbation theory, again, going from the first principle. So that's the plan for the next week. Okay, let me stop here. That's the end of the class today, but I await for additional questions.
I just wanted to ask, where do we get the selection rule again, that delta L must equal to 1?
That's right. So X is a vector, and the vector is basically an operator that carries angular momentum 1. So when you actually go from initial to the final state, let's say initial state has angular momentum L, you need to add angular momentum L and 1, and that, as you know, would result in 3 possibilities: angular momentum L minus 1, L, or L plus 1. So at this stage, there may be still a possibility that the initial and final state have the same angular momentum. But it turns out that there's yet another property of this electrodipole moment operator, which is that this flips its sign under parity, inversion of space, x goes to minus x. So by definition, x goes to minus x, and therefore dipole operator is odd under parity. And for a given state of orbital angular momentum L, parity is minus 1 to the L. So when you have this initial state I with angular momentum L, parity is minus 1 to the L, but dipole operator is odd under parity, so that's minus 1. So total parity of initial state with a dipole operator acting on it would have parity minus 1 to the L times minus 1. So in order to have the same parity for the final state, then the final state cannot have the same orbital angular momentum L, because that would give you the opposite parity. But if the final state has angular momenta either L minus 1 or L plus 1, that has the correct parity so that this matrix element does not vanish. If you just go ahead and do the integral between explicit wave functions, then the case of the odd parity actually turns out to be just an integral of an odd function so that it identically vanishes. So that gives you yet another selection rule. Not only that final states need to have the correct angular momentum, L minus 1, L, or L plus 1, you don't have also the correct parity. The case of L is excluded now, so that final state has angular momentum either L minus 1 or L plus 1. That's what I meant when I said delta L has to be 1. And that's yet another reason why 2s state cannot decay into 1s state, even if you keep the higher powers in e to the exponential iqx.
Okay, makes sense.
Well, thanks for the question. Any other questions here? Good. Okay, so I hope you're doing well with the midterm problems, and the deadline is coming up soon. So good luck with that, and I see you again next week. So have a good weekend.